Very good afternoon, students.
Good afternoon, sir.
Good afternoon.
So let us start the discussion without wasting any time. If you remember last class, we have discussed about this oxymercuration demercuration. Today we are going to start with the hydroboration oxidation reaction. As I have told you, hydroboration oxidation is also just an addition of water to your alkene molecule, and the mechanism proceeds through four-member transition state. And BH3 in the presence of THF is the hydroboration reaction, and the H2O2 in the presence of OH- is the oxidation reaction. And the hydrogen is actually added from the BH3, and H2O2 in the presence of OH- we get a OH group added. And the addition of water occurs according to anti-Markovnikov rule. No rearrangements are possible because carbocation is not the intermediate. The same things. So RCH double bond CH2 BH2H gives RCHH CH2 BH2 treated with H2O2 in the presence of OH- forms RCHH CH2H. These steps are very high. As I have told you previously also, the oxidation step is very high. So very high number of steps are there. That's why that is not required. But you can think of H2O2 in the presence of OH- will give addition of OH. Anti-Markovnikov addition is going to happen. Is that clear, students?
Yes, sir.
Yes, right. In this reaction, addition of water takes place. By anti-Markovnikov addition of water and alcohol is formed. No carbocation intermediate is formed, so rearrangement do not take place. So try to solve this question. CH3, CH2, CH double bond CH2, BD3 in the presence of THF, and then H2O2 in the presence of OH-. What is the final product?
CH2, CH3, CH2, CHD, CHOH.
Yes, very good. CH3, CH2, CHD, CH2OH. Right? Because we have taken BD3, so deuterium is going to be added instead of hydrogen, and anti-Markovnikov addition. So OH should be added because H2O2 in the presence of OH- is taken. H2O2 in the presence of OH- is taken. So ultimately your product will be CH3, CH2, CHD, CH2OH. Right? So this will be a major product. Very good. For above conversion, reagent exists. For the above conversion, that alkene is there and you are getting an alcohol. So you can think of a reaction of addition of water. Addition of water means three things should be coming to your mind. Addition of water in the presence of dilute acids, where carbocation is intermediate. Addition of water according to oxymercuration demercuration, where Markovnikov rule is followed. Addition of water according to anti-Markovnikov rule, that is addition of water according to anti-Markovnikov rule is happened in hydroboration oxidation. So here OH is added to this particular carbon atom which has more number of hydrogens. This carbon do not have hydrogen. So for this, you can just go with the reagent. Which type of reagent can I choose? If I take a dilute H2S4, then carbocation should be formed, then OH should be added here because 3-degree carbocation is more stable. Answer only 3 is possible because 1 and 2 will lead to the other products. 1 and 2 will lead to the other products. So next type of reactions of alkenes after the free radical, after the electrophilic addition reactions, we also have free radical addition reactions. In the free radical addition reactions, what you can think of is addition of HBr. Okay, peroxide effect or Kharash effect, we can say. Addition of HBr in the presence of a peroxide follows anti-Markovnikov rule, and the reason for that is it is proceeding through free radical path. And why only HBr? Because HF and HCl bonds are stronger. HI is a weaker bond, but I dot molecules, the I dot free radical, iodine free radical will combine with other free radical to form iodine, I2. So only HBr addition. CH3, CH double bond CH2 treated with HBr. The pi electron density attacks H plus to form a carbocation. bromide ion will be acting as a nucleophile. It attacks the electrophilic carbon, generating Markovnikov product. In the first case, there is no peroxide, so it will be carbocation intermediate. Okay, proceeds through carbocation. But if the same reaction you done in the presence of peroxide, it will proceed through free radical mechanistic approach. Okay, the second reaction is proceeds through free radical path. Okay, so we have CH3, CH8, CH2Br, which is nothing but your anti-Markovnikov product. Reaction of alkene with HBr in the presence of peroxides takes place through free radical mechanism, and this is an example of free radical addition because the addition happened ultimately. It is not substitution, it is an addition reaction. And what was the mechanistic approach you can think of? Like we have a peroxide, right? What type of mechanism I have told you earlier? Like peroxide, you can take H2O2 or R2O2, ROOR, peroxy bond is there. That upon treatment with sunlight, it will cleave homolytically, generating RO dot plus RO dot. RO dot plus RO dot is nothing but 2 RO dot. The RO dot will be reacting with HBr. Now abstraction of H dot from this will generate ROH plus Br dot. ROH plus Br dot. This is the general mechanistic approach. The Br dot which is formed, that will now react with the alkene system. Let us take an alkene CH3, CH double bond CH2 treated with Br dot. So the pi electron density, you can imagine one electron to this carbon, other electron to the other carbon. So this carbon has one electron, this carbon can also have one electron. So if the one electron, the terminal carbon reacts with Br dot, then you will generate a 2-degree free radical. You can generate a CH dot CH2Br plus CH3 CH Br CH2 dot. So this is primary, this is secondary. Secondary free radical is more stable. So this secondary free radical which is more stable, that will be formed, that will react with HBr again. That will react with HBr again to form CH3 CH2 CH2Br, and Br dot is released. That Br dot will react with one more molecule to generate same type of species. So this is nothing but your major product. Reaction of alkene with HBr in the presence of peroxide takes place through free radical mechanism, and this is an example of free radical addition reaction. This is an example of free radical addition reaction. Peroxides, you can take H2O2, R2O2, C6H5, C double bond O, C double bond C6H5, benzoyl peroxide. All such peroxides you can take. CH3, CH double bond CH2, HBr in the presence of R2O2. Is that clear, students? Whenever you are treating with the HBr is treated with the R2O2, you will generate CH3, CH2, CH2Br. This will be your major product, and the mechanism is free radical path. This is a mechanism, whatever I have given, that is nothing but the mechanism. Same mechanism we have seen earlier. Like whatever the peroxy radical obtained, RO dot, that will abstract the H dot to form halogen radical. That halogen radical will react with the alkene in such a way such that you will get a secondary secondary free radical. That secondary free radical, why it is formed? Since it is more stable. Why? Due to more number of hyperconjugative structures. What can which compounds can undergo hyperconjugation? Free radicals, carbocations, alkenes. Carbanions will not undergo hyperconjugation because there is no vacant orbitals. Is that clear, students?
Yes, sir.
Yes.
Yes.
Yes, let us look at the same mechanism, whatever I have discussed. So peroxide we have taken. So we get the RO dot. That RO dot will pick up the H dot. Homolytic cleavage occurs. You will generate ROH plus Br dot. CH3 CH double bond CH2 plus Br dot. It will now form CH3 CH dot CH2Br, secondary free radical, which is more stable due to more number of hyperconjugative structures. And that secondary free radical will be reacting with HBr. Again, homolytic cleavage occurs. A hydrogen radical react with the alkyl radical to form respective haloalkane CH3, CH8, CH2Br plus Br dot, which is nothing but your major product. CH3, CH2, CH2Br, that is nothing but your major product. The same mechanism, whatever we have studied in the previous slides. Reasons: it may be noted that peroxide effect is not observed in addition of HCl and HI. This may be due to the fact that HCl bond being stronger than HBr. Same with the HF. HF is not taken into account. HF bond is even stronger. HCl bond being stronger than HBr is not cleaved by free radical, whereas HI bond is weaker and iodine free radicals combine to form iodine molecules instead of adding to a double bond. Like if I give a question to you in this manner, CH3, CH double bond CH2 treated with HCl in the presence of R2O2. What is the mechanism of this particular reaction?
Come on, Atika.
What is the mechanism of this particular reaction? If you go with the mechanistic approach, RCH double bond CH2 treated with HCl in the presence of peroxide. What will
According to
happen?
Markovnikov's rule,
Yeah, according to Markovnikov rule, we can write the product, but what is the mechanistic approach I'm asking? Like what is the intermediate in this particular reaction?
carbocation.
Carbocation. Okay. CH3, CH double bond CH2, since R2O2 is not able to cleave the HCl bond homolytically, so whatever the HCl we have, that is affected by the pi electron density, and it will lead to the generation of carbocation, leading to CH3, CH plus, CH3, and a chloride ion is lost in the previous step. That chloride ion which is lost, that is now going to attack this particular carbon, generating CH3, CHCl, CH3, which is nothing but your major product. Okay, which is nothing but your major product. So whenever you treat the HCl in the presence of peroxides, the mechanism proceeds through carbocation approach, not the free radical approach, because free radical cannot be formed because HCl bond is a stronger bond when compared to HBr bond. Only with HBr, peroxide effect is going to happen. Right? Try to solve this question. What happens in the two cases? What is the product in option A? Like HBr alone, HBr treated with R2O2. I can say in the first option, it will be CHBr,
CH2, CH3.
CH3. In the second option, what I can say?
C. Benzene ring CH, CH2Br.
Benzene ring CH2, CH2Br. If you think like this, you try to write the mechanism approach, mechanistic approach. If you go with the mechanistic approach, you will be getting a benzyl free radical or not in the second option.
Yes, sir.
Yes or no? Benzyl free radical is not going to be stable. Like I want to generate HBr, although the products were given in this fashion. You think on this question. HBr treated with R2O2. R2O2 initially form what? 2RO dot. HBr treated with RO dot will form ROH and Br dot. That Br dot is now going to be reacting with the CH double bond CH2 Br dot. If a Br dot is reacting with this, it will form what type of free radical? CH dot CH2Br. Yes or no? This is benzylic free radical, which is even more stable. So this will finally react with HBr to form respective compound CH2, CH2Br. Everyone got this or not?
Yes, sir.
Yes.
So here, whatever the free radical obtained is not just a secondary, it is a benzylic free radical, which is even more stabilized by resonance. So obviously that will be your right answer. Right, product of free radical will be opposite to that of product of electrophilic addition reaction. Next set of reactions of alkenes, if you look at oxidation reaction. Reactions involving oxidation of carbon-carbon double bond may be classified into two general groups. What are those? Oxidation of pi bond without cleavage of sigma bond, and oxidation of both sigma and pi bond. Oxidation of pi bond with the cleavage of sigma bond is both sigma and pi bond are cleaved. Oxidation of pi bond alone without any cleavage of sigma bond. So can you think of any reaction coming under the first category? Oxidation of pi bond without cleavage of sigma bond. You can use a Bayer's reagent, cold and dilute alkaline KMnO4. What happens if you try to use Bayer's reagent? Bayer's reagent, anyone know what is Bayer's reagent? Cold and dilute alkaline KMnO4. KMnO4 means it will have MnO4 minus ion, permanganate ion. Yes or no? This MnO4 minus ion will try to attach to the carbon-carbon double bond in such a way such that it will be undergoing a syn attack or the anti-attack. You try to answer this. Like if you think of any alkane, like I have taken alkane like this, CH3, CH, like let us take butene. Simple example. Butene means I can have cis-butene, trans-butene. I have taken cis-butene. I have taken cis-butene. This cis-butene I am trying to add with KMN4. What will happen? If I treat this with a Bayer's reagent, CH3, CH double bond, CH, CH3, Bayer's reagent is cold and dilute alkaline KMnO4. The MnO4 minus whatever it is there, that will now try to be affected with the pi electron density. The charge transfer is occurring. The pi electron density of alkene is now going to be forming a 5-member ring complex. It will form such type of complex CH3, carbon-carbon double bond, whatever is there, sigma and pi bond. The pi bond is now going to be broken, but the sigma bond will lie as it is. Sigma bond will lie as it is, and the pi bond is now going to be broken. It will react with the MnO4 minus to form a species like this: O, MnO, Mn double bond O minus, Mn double bond O minus. This is a 5-member ring structure, and this after treating with water, after several steps, you will get a hydroxylation: CH3, CH, OH, C, CH3, COH, CH. CH3, CHOH, CHOH, CH3. This is nothing but your major product. So diols are going to be formed, or glycol system is going to be formed, and MnO4 minus is ultimately converting into MnO2. MnO4 minus is now going to be converted to MnO2. MnO2 is actually brown in color. MnO4 minus KMnO4. What is the color of KMnO4? You might have done the titrations and all.
Dark purple.
Purple.
Purple in color. Yes or no? So MnO4 minus, which is in purple color, that is added to the pi electron density and forming MnO2, which is brown color. So the color change, can we say because of this color change, can we say that the compound has unsaturation or not? It is also a test of unsaturation. I can say alkenes plus MnO4 minus cold and dilute, or you can say Bayes reagent, will form some respective glycols, glycol systems plus MnO2. The MnO4 minus, which is actually purple in color, that will change to brown colored precipitate. The purple colored permanganate changing into brown precipitate will give the idea that the initial compound, whatever we have taken, that has unsaturation. It is a test of unsaturation. And if I take a cis alkene, what is going to happen? We all know CAR, cis alkenes undergoes anti-addition use sp mixture. Cis alkene undergoes syn addition use meso compound. What type of addition is this? Addition of KMnO4 is syn. Addition of KMnO4 is syn, because from the same side the two oxygens should be attaching to the carbon atoms to form the 5-member ring. If they are opposite side, the ring is not stabilized. Addition of KMnO4 is syn addition. Cis alkene have taken cis-butene undergoing syn addition use meso. So whenever cis-butene reacts with the alkaline KMnO4, cold and dilute alkaline KMnO4, it will give meso compound. Understood this point or not? Let us understand the same thing. So hydroxylation using Bayes reagent, cold and dilute alkaline KMnO4. So I have taken alkene like this, treated with KMnO4, MnO4 minus. MnO4 minus will form a 5-membered complex like this: 1, 2, 3, 4, 5, with 1 manganese, 2 oxygens, and 2 carbons in the ring. That upon treatment with water, after long steps, it will form respect to glycol, like 2 OH groups are present on 2 adjacent carbons, and MnO2 is released. As I have told you, this reaction is used as a test of unsaturation. Why? Because base reagent is purple in color. As the reaction proceeds, the purple color disappears and a brown PPT of MnO2 forms, because MnO2 is obtained, which is a brown precipitate. Is that clear, students?
Yes,
With a
sir.
dilute KMnO4, this reaction occurs. With the dilute KMnO4, this type of reaction occurs. You can just look at the same in the animation. Alkene and alkyne treated with the Bayer's reagents. Just look at the animation, all of you. Bayer's reagent was added. And you can see the brown PPT formation that indicates the presence of unsaturation, that is carbon-carbon pi electron density is present in that particular compound. Yes or no? The test of unsaturation, this is shown by alkenes and alkynes both. Example, CH2 double bond CH2 dilute KMnO4. It will form what? Dilute KMnO4, ethylene, ethane 1, 2 diol, or ethylene glycol, you can say. So the product will be CH2, CH2, OH, OH. CH3, CH double bond CH2 dilute KMnO4 270 Kelvin. What is the product? CH3, CH, OH, CH2, OH. I can say propane 1, 2 diol. Propane 1, 2 diol. What happens here? Base reagents. The pi bond is going to be broken and 2 OH groups are going to be added. And what type of addition you are going to get?
Syn addition.
So you'll get meso compounds. Yes or no? You will be getting meso compound. Like both the OH groups, they should be on the same side. Next set of reaction, oxidation of pi bond with cleavage of sigma bond as well. So any reaction, do you remember where sigma bond is also cleaved? Both pi bond and sigma bond. Very famous reaction. Ozonolysis. Very good. Very famous reaction. RCH double bond C, RR. If you try to treat this with O3 in the presence of H2 and zinc, you have the cleavage. Ozonolysis is actually classified in two types: reductive ozonolysis and oxidative ozonolysis. Reductive ozonolysis means you can also take ozone in the presence of zinc and water, or H2O2, or Me2S, dimethyl sulfide. If you want to do oxidative ozonolysis, you have to take just O3 ozone in the presence of water. Ozone in the presence of water, you will just get what do you call oxidative ozonolysis. The first one is reductive ozonolysis, and the second one is oxidative ozonolysis. Why it is so? Because the mechanism, if you try to observe, the ozonide is going to be formed. Yes or no? So if you try to look at the mechanistic approach, students, R, C double bond C, CH, R we have taken, right? This has been treated with ozone. What happens is ozonide is going to be formed, where both the single, that is sigma and pi bond, are going to be broken, and you will have this type of structure. And you will have this type of structure. Ozonide is going to be formed, because by drawing the shape of ozone, you can understand, like O double bond O. With respect to this shape, you can say ozone is going to be added to this pi electron density in such a way such that ozonide is going to be formed. This ozonide is unstable. It will undergo cleavage in such a way such that it forms the respective carbonyl compounds. Let us do the reaction in the presence of H2O in the presence of zinc as well. Yes or no? H2O and zinc. So what happens now? Because ozonide is unstable, we have water, right? So the bonds are going to be cleaved in such a way such that one oxygen is going to be lost. Such that one oxygen atom is going to be lost. So you will get R C double bond OH plus R C double bond OH, and whatever the extra oxygen we have, that is taken by H2O to form H2O2. That H2O will take up, along with this reaction, the water will take up the nascent oxygen to form H2O2. Understand this reaction carefully. Whenever ozonide is formed, ozonide will undergo cleavage in such a way such that every carbon which earlier have a carbon, which earlier involved in a carbon-carbon double bond, will now get a C double bond O. Whenever we treat this with a, whenever ozonide undergoes cleavage, every carbon which was earlier having C double bond C ring, they were getting carbon double bond O. And we have one extra oxygen. That oxygen is taken by water to form H2O2. If we have zinc or dimethyl sulfide, that zinc will react with H2O2 to form ZNO, zinc oxide, and H2O. Water is formed back. If we do not have zinc or if we do not have Me2S, this H2O2 will be present in the reaction mixture only. If H2O2 is present in the reaction mixture, that will act as an oxidizing agent and it will oxidize the respective aldehydes to acids. Ketones are not oxidized. Ketones are not oxidized as the oxidation of ketones involve cleavage of carbon-carbon bond. But whatever the aldehydes we have, RC double bond H is an aldehyde, right? This subbond it with H2O2. If we have zinc, then the reaction will stop here only, reduct to ozonolysis we can say. If we do not have zinc, then the further oxidation occurs to form RC double bond OH. Everyone got this or not?
Yes. Yes.
Okay. So O3 in the presence of H2 or zinc in the presence of Me2S, it will follow reduct to ozonolysis. O3 just H2O, it will undergo oxidative ozonolysis. And you have to undergo in the oxidative ozonolysis, it is not always sure that we should get an acid. It depends upon the type of alkene we have taken. Instead of hydrogen here, if I have taken any alkyl group R, here also I will be getting alkyl group R only because ketones, both the ketone molecules are going to be obtained. Yes or no? And can we oxidize ketones? Ketones are not oxidized to carboxylic acid easily. Right on that point. Ketones are not oxidized to acids with milder oxidizing agents. But can be oxidized, but can be converted to acids, in the presence of KMNO4 or K2Cr2O7. Anyone remember there is a rule which decides the oxidation of ketone? What is that rule called as? Oxidation of ketone, like unsymmetrical ketone if I have taken, that unsymmetrical ketone oxidation will be happening in such a way such that the C double bond O has to be always lie with the smaller alkyl group. This is nothing but Popov's rule. Yes, Popov's rule, very good. Okay, where you will study Popov's rule. We will study about this rule in carbonyl compounds, where we are going to discuss about the oxidation of ketones. Oxidation of aldehydes can we do? What are the milder oxidizing agents where aldehydes can be oxidized? What are the milder oxidizing agents where you can oxidize alcohols to carbonyls? Alcohols I have to convert, I want to convert to respect to carbonyl compounds. What are the milder oxidizing agents? Anyone remember or not? PCC, PDC.
PCC and CrO3.
Yeah, PCC, PDC, CrO3 in the absence of water. And what are the milder oxidizing agents where you can convert the carbonyls to respect to acids? Tollens reagent. Yeah, Tollens reagent, Bendix reagent, Fehling solution. Very good. Okay. Similarly, you cannot oxidize the ketones to respect to acids or carboxylates with the milder oxidizing agents because in ketones there is no oxidizable hydrogen. If you want to oxidize, you have to cleave the carbon-carbon bond. To oxidize ketones, you have to use Popov's rule. According to Popov's rule, if you have a compound like this, like CH3, C double bond O, CH2, CH2, CH3, we have to oxidize this. The oxidation of ketones, unsymmetrical ketones, will happen in such a way such that the C double bond O always lie with the smaller alkyl group. Which is smaller alkyl group? CH3 is smaller when compared to propyl. So which bond is going to be cleaved? I can say this is A, this is B. Which bond will cleave?
B.
B, because C double bond O has to lie with the smaller alkyl group, so only bond B is going to be broken. So when you try to oxidize this particular compound, this particular ketone, like in the presence of KMnO4, you will get a CH3 C double bond OH plus a C double bond OH CH2 CH3. So this is the correct set of products obtained, right? And you won't be getting formic acid and butanoic acid. You will be getting ethanoic acid and propanoic acid as a correct set of products. Like which bond has to be cleaved in the oxidation of unsymmetrical ketone is given by Popov's rule. Right, students? Let us proceed further. So RCH double bond CRR. As I have told you, it will form ozonide. That ozonide, if you treat with zinc in the presence of water, zinc in the presence of water means reducto-ozonolysis. So to each carbon, you have to connect the respective C double bond O, RC double bond H plus RC double bond R. If you have just water, you don't have any zinc or dimethyl sulfide, then what happens? Then you will get oxidative ozonolysis. You will get RC double bond H plus RC double bond R plus H2O2. That H2O2 which is obtained, that will again act as an oxidizing agent, and it will try to oxidize the respective aldehydes to respective carboxylic acids. But here in the previous step, whatever the H2O2 obtained, that will react with zinc to form zinc oxide and H2O. And we all know zinc has a tendency to undergo oxidation. Why? Because that depends upon the crystal lattice structure of zinc, metallic bonding, heat of atomizations. Based on all those, we can say it has a good reduction potential to undergo oxidation. So reductive ozonolysis happens, and oxidative ozonolysis will lead to the formation of acids as well. In oxidative ozonolysis, oxidation of aldehydes takes place while oxidation of ketones does not take place, because ketones, if you want to oxidize, you have to cleave the carbon-carbon bond. If a formic acid is formed in oxidative ozonolysis, then it further oxidizes to CO2. If formic acid is formed, Hc double bond OH, it will again oxidize to CO2. Hc double bond OH in the presence of oxygen forms CO2 and H2O. Try to solve this question. CH3, C double bond CH2, O3, zinc and H2O means reductive ozonolysis. Reductive ozonolysis means you can cleave both the bonds, and to each carbon you have to connect a C double bond O. What is A? CH3, C double bond O, CH3 plus H, C double bond O, H. This is the set of products in A. What about B? You first write the compounds. In B, you will get CH3, C double bond O, CH3 plus H, C double bond O, H. This Hc double bond H is nothing but formaldehyde. We have H2O2 also produced. That H2O2 will react with formaldehyde to form HC double bond OH. This Hc double bond OH, whatever it is formed, that will again oxidize to form CO2 and H2O. So in compound B, in the set of products of B, you get acetone and CO2. In A, we'll get acetone and formaldehyde. Got it now?
Yes, sir.
Yes, right. So try to solve similar questions. What are A and B? A, I can directly write zinc is there. So acetone CH3, C double bond O CH3 plus HC double bond O CH3. In B, the HC double bond O CH3 is again going to be oxidized. In the presence of H2O2, it will form CH3, C double bond O OH. A will be CH3, C double bond O CH3 plus CH3, C double bond OH. B will be, first you will get CH3, C double bond O CH3 plus CH3, C double bond OH. That will again oxidize to form respective acid. This is acetic acid. So acetic acid cannot oxidize to give respect to carbon dioxide, but formic acid can give to form respect to carbon dioxide. Right? These are very famous reactions. Many times these reactions, ozonolysis can be combined with another reaction, famous reaction. Can anyone remember? Lot of questions we can frame combining ozonolysis and intramolecular aldol. Like I'll give you a simple example. I have given a molecule to you in this manner. CH3, CH3 double bond. First I'll treat this with a first set of reagent is O3. Second is Me2S. Or I can just write down this product. Okay, first set is NaNH2. Second set is O3. Third is Me2S. Fourth is dilute OH minus. Fifth is heating. NaNH2 treated with this particular compound, what will happen? Try to understand. NaNH2 treated with this particular compound, what will happen in the first reaction? NaNH2 strong base undergoes what type of reaction? Elimination will occur.
Elimination.
Yes or no? Elimination will occur. After first you will get this type of product. After treating with NaNH2 you will get this type of alkene. Now O3 in the presence of Me2S. O3 means you will get ozonide. Me2S react to ozonolysis. You will get what? You have to break carbon-carbon double bond, that is both sigma and pi you have to break, and each carbon you have to connect it with C double bond O. You will get C double bond O. You get C double bond O CH3. It is what, dicarbonyl or not? This dicarbonyl compound can be treated with the dilute OH minus. So dilute NaOH or dilute KOH, Na2CO3, K2CO3, all those weak bases can be reacting with dicarbonyls to undergo aldol condensation, intramolecular aldol. Okay, it further undergoes intramolecular aldol. I am not writing the mechanism of intramolecular aldol as of now because we have not discussed that reaction. We'll discuss that in carbonyl compounds, but very famous ozonolysis. Elimination can be done to produce alkene. Alkene can undergo ozonolysis. Ozonolysis can be producing a dicarbonyl if I take in a cyclic compound. The dicarbonyl can be treated with again intramolecular aldol to form respective 5-membered or 6-membered products. And you will get alpha beta unsaturated products also because heating has been mentioned. Okay, that is how the reactions can be combined, students. So be perfect with this aldol as well. So here what are set of products obtained? You have to cleave this. You will generate 2 molecules of CH3, C double bond O CH3. Again you have CH3, C double bond O CH3. CH3, C double bond O CH3 plus CH3, C double bond O CH3. What happens here? Both the sigma and pi bond are going to be broken. You will get C double bond OH, C double bond OH. Right, that is the dicarbonyl obtained. What happens in this case? CH2 double bond C double bond CH2. What will happen in this case?
Two moles of HCHO
Yes,
and 1 mole of carbon dioxide.
very good. Because these 2 bonds are going to be broken. HC double bond H and direct to ozonolysis. And you will get CO2. This carbon is not having any hydrogens. It will convert to CO2. And direct to ozonolysis, this HC double bond H will be lying. It is not converted to respect to formic acid. And you will get 2 moles because you have 2 terminal carbons. Right. Benzene treated with O3 in the presence of zinc and H2O. What you will get? I can cleave this bond as well as this bond as well as this bond. So if I cleave this bond, this carbon will get double bond O. This carbon will also get double bond O. So can I say C double bond OH, C double bond OH? How many such moles should be obtained? 3 moles. 3 moles of C double bond OH, C double bond OH, which is nothing but a glyoxal. Here, orthoxylene. So you have to be careful because the double bond positions were not known to you. So double bond positions, based on the difference in double bond positions, you will get different types of products because substitution is there. If I consider this type of presence of double bonds, and the other type I can also consider in this fashion, then I'll be getting different set of products, right or not? So if I
Yes.
consider this type of product, I'll be getting, like I have to cleave these bonds, C double bond OH, C double bond OH, C double bond OH, C double bond of CH3, C double bond OH, C double bond of CH3. So 2 moles of C double bond of C double bond of CH3 and 1 mole of C double bond OH, C double bond OH. If I take other sets, I'll be getting C double bond of CH3, C double bond of CH3, 1 mole, and 2 moles of 1 mole of C double bond of CH3, C double bond of CH3, and 2 moles of C double bond of H, C double bond of H. So these are the set of compounds obtained. This is nothing but orthoxylene, because they have not mentioned the positions of double bond. You should be careful with like what are the possibilities. If we asked, we have to list out all the possibilities. You should not be going with only one option. You should list out all the possibilities. You should not go with the only one option, right? Different reactions of ozonolysis. These are different examples. Can you try this? 8th one and 9th one, take as homework. All the answers are there. You just try it on your own. Next set of reagents is using strong oxidizing agent, that is KMnO4 in the presence of H plus or K2Cr2O7 in the presence of H plus. What is going to happen? Strong oxidizing agent, I have discussed about base reagents. So cold and dilute alkaline KMnO4 will form glycol systems, like two carbon atoms which were involved in the carbon-carbon double bond. They'll get two OH groups added. But now acidic KMnO4 or acidic potassium dichromate oxidizes alkenes to respective ketones as well as acids, depending upon the nature of alkene. Like if I take an alkene like this, CH3, CH double bond, CH, CH3, what will happen is you will have the cleavage of this carbon-carbon, both sigma bond as well as pi bond. You will get CH3, C double bond OH. First, you will get similar to your respective ozonolysis. You have to write the products. You will get CH3, C double bond OH, and CH3, C double bond OH. They can further oxidize or not, because CH bond is there. CH bond can be cleaved again. This is oxidizable hydrogen. It will convert CH3, C double bond OH. It will also convert to CH3, C double bond OH. So you get 2 moles of ethanoic acid whenever you treat butane with KMnO4 in the presence of acidic condition. Acidic KMnO4 will be acting as a strong oxidizing agent. It will react with alkene to form respective carbonyl compound or acid that depends upon the type of alkene we have chosen. We have to just cleave the carbon-carbon sigma and pi bond both. Look at the respective carbonyls. If it is an aldehyde, oxidize the aldehyde. If it is a ketone, do not oxidize the ketone. You may ask a question, sir, here we have KMnO4H plus K2Cr2O7. Then why can't ketone be oxidized? We are not treating directly ketone with KMnO4. The alkene has been treated with KMnO4 and ketone is formed. If we treat ketones directly with the KMnO4 or K2Cr2O7, they can oxidize according to Popoff's rule. But here oxidation of ketone is not accepted, right? So butene KMnO4, you get ethanoic acid 2 moles, and you have 2-methyl propene KMnO4 in the presence of H plus. What happens? You cleave this bond, you will generate what type of products? You will have CH3, C double bond to CH3. This is a ketone, and you will have HC double bond to H. HC double bond to H is an aldehyde, whereas ketones cannot be oxidized. This aldehyde can be converted to HC double bond OH. Whenever we get formic acid, that will be converted to respective carbon dioxide. So you get CH3, C double bond to CH3 plus CO2 plus H2O, because oxidation happened. Yes or no? In the second case, you will get CH3, C double bond to CH3 plus CO2 plus H2O. So those are the set of compounds obtained. Is that clear, students?
Yes, sir.
Yes or no? These are the oxidation of alkenes using strong oxidizing agent, that is KMnO4 in the presence of H plus or K2Cr2O7 in the presence of H plus. If you take a KMnO4 in the presence of alkaline medium and cold and dilute condition, then only it will form glycol system. If H plus medium is taken, it will act as strong oxidizing agent. It will form respective aldehydes as well as your acids. That depends upon the type of alkene we have taken. Then comes the last set of reactions of alkenes, polymerization reaction. You all have studied polymers. Polythene generally is obtained from ethene. If you take propene, you will get polypropene. Yes or no? So polythene or polypropenes, they are actually obtained from alkenes. And alkenes will undergo polymerization. What type of mechanism? Addition polymerization or condensation polymerization alkenes will undergo? Alkenes will generally undergo addition polymerization because the molecules are simply added. There is no loss of simple molecules like water or alcohol. But if you take any functional groups, yes or no? So there are two categories of polymerization reactions: addition polymerization and condensation polymerization. Alkenes mainly undergo addition polymerization reactions. Polythene is obtained by polymerization of ethene molecules at high temperature, high pressure. High temperature and high pressure is required, and also a presence of catalyst. Different type of polymer preparation requires different types of catalysts. HDP, LDP will study the details in polymers. Large molecules that thus obtained are called polymers, and simple compounds from which polymers are obtained are said to be monomers. Like if you take a NCH2 double bond CH2, that is N molecules of ethene you have considered, CH2 double bond CH2. Upon polymerization, what happens? You will have CH2 is repeated n times. There's a difference. If I take NCH2 double bond CH2, these are N monomer units. Upon polymerization, they will form CH2 taken, and that means a polythene is obtained where the carbons are simply connected to the next two groups. This is a repeating unit. So this bracket and n time, that is nothing but a repeating unit. NCH3 CH double bond CH2. If you go with this example, high temperature or pressure and catalyst, you have to write this carefully. You should not write this as CH2 CH single bond CH. This is wrong. This is wrong. Because here the pi electron density, whatever you have, that is actually connected. So this methyl is substituted this particular carbon atom. So this carbon which is involved in the pi bond, that is now having one CH bond as well as CH substituent. The other carbon has CH2, and those are repeated. It is not CH2 taken in. It is CH3 CH2 taken in. This is nothing but your polypropene. The way you have to write the polymer, that has to be properly mentioned. Is that clear?
Yes, sir.
Yes.
If you write the same polypropane in this fashion, that is wrong, because the pi electron density is present between only two carbons, but you are repeating this three carbon system, which is obviously wrong, where CH3 is just a substituent. So these are the polymerization reactions, students. We have different other reactions also: terephthalic acid, adipic acid, nylon 6,6, caprolactam. Yes or no? Different monomers, different polymers are seen. Bakelite, Novolac. Yes or no? Glyptal. All that we'll discuss in the polymers. Polymers are everywhere, right? Every day we are dealing with a lot of things. Is bottles, caps, mugs, hair, DNA, RNA, everything is a polymer. Yes or no? The polymerization modes, you have to think. What type of polymerization is going to happen? There's a reaction, organic reaction happening between the molecules in the presence of a catalyst. The role of catalyst is increase the rate of reaction. How can it increase the rate of reaction? By decreasing the activation energy. So different methods are there. We'll be discussing all those details in the respective chapter. Then comes the use of polymers. Polymers are used for manufacture of plastic bags, squeeze bottles, refrigerators, everything, TV cabinets and all. Polypropylene is used for the manufacture of milk crates, plastic buckets, and other molded articles. You have to remember these usages, students. So there is no shortcut in that. You have to remember. Okay. Especially you have to remember the uses of specified polymers, whatever we are going to study in our chapter. Okay. So then comes the next type of hydrocarbons, alkanes. Again, for alkanes, we will be looking with methods of preparation, physical properties, and chemical properties. Methods of preparation. Can you think of any methods of preparation? Alkynes, vicinal dihalides, geminal dihalides we can prepare. Commercial method we can prepare from calcium carbide, CaC2 upon reacting with H2O, it forms acetylene. CaC2 upon reacting with D2O, it forms C2D2. CaC2 is obtained by heating limestone and producing CaO. Yes or no? Heating limestone, if you heat limestone, what will get? You will get a calcium oxide. That calcium oxide upon treatment with the carbon will get CaC2. Vicinal dihalides, geminal dihalides from calcium carbide, from chloroform, treatment with silver powder in the presence of heating. These are the four main techniques from where you can actually prepare the respective alkynes. Let us look at those techniques. Vicinal dihalide upon treatment with alcoholic OH undergo dehydrohalogenation. Same thing, because alcoholic OH has to undergo elimination to form alkenyl halide, which on further treatment with soda amide gives alkyne. We have CHBr. We are treating this with alcoholic OH. Alcoholic OH, what it will do? The OH minus picks up the proton. As soon as the proton is picked up, the CH electron density comes into carbon bromine bond leaves. So what will happen now, students? OH minus picks up this particular proton, CH electron density come, bromide ion left. That bromide ion will develop electrostatic force of attraction with K plus to form KBr. OH minus picked up the proton, so water is also formed. So you get RCH double bond C, R and Br. Now it has treated with NaNH2. You should not just treat with alcoholic OH. If you just treat with alcoholic OH is a strong base, but not a very strong base to convert this alkenyl halide to alkynes. But after alcoholic OH, you have to use very strong base like NaNH2. The NH2 minus will now try to pick up this proton. CH electron density comes into CBr leaves. So you get what? RC triple bond, like bromide ion will react with Na plus to form NaBr. NH2 minus picked up the proton, NH3 is obtained. You get RC triple bond Cr. R C triple bond Cr is going to be obtained. Is that clear, students?
Yes, sir.
Yes, sir.
Yes. Vicinal dihalide, if you have taken in this manner, so what type of compound is obtained? You can also treat with 2 moles of NaNH2, not an issue, but you cannot treat with alcoholic OH alone. If you are treating with alcoholic OH, you get alkenyl halide. To convert the alkenyl halide, you have to treat with NaNH2. But directly the vicinal dihalide, you can start the reaction with NaNH2 and get to the desired product, because NaNH2 is a strong base. Right? Geminal dihalides. Geminal dihalides means what, students? Geminal dihalides means the two halogen atoms are connected to the same carbon. And in the case of geminal dihalides, if that carbon is a terminal carbon, we will have respect to salt formation also. We have to think carefully, because geminal dihalides also again treat with alcoholic OH, again treat with NaNH2, you will be getting respect to alkynes. Alcoholic OH minus picks up this proton, CH electron density comes into carbon bromine bond leaves. You get alkenyl halide, NH2, Na plus NH2 minus. NH2 minus picks up the proton, this carbon hydrogen bond comes into carbon bromine bond leaves. You get RC triple bond Cr. RCH2 CBr or NaNH2. It will form again same Na plus NH2 minus. You can treat with 2 molecules of NaNH2 as well. Picks up the proton, CH electron density comes into CBr leaves. NH2 minus picks up this proton, CH electron density comes into C bromine leaves, bromide leaves. RC triple bond Cr. You can treat with alcoholic OH followed by NaNH2, or you can treat with the 2 moles of NaNH2. You will be getting respect to alkynes. But in case if you take this type of species, R CH2 CBr CH, treat with NaNH2, what will happen now? R CH2 CBr NH2 minus picks up this proton, CH electron density comes into carbon bromine leaves. We get RCH C double bond C CBr CH. Again treat with NaNH2. NH2 minus picks up this proton, CH electron density comes into carbon bromine leaves. We get RC double bond C CH. But still it is a sp hybridized carbon which can be reacting with NaNH2 to form RC triple bond C minus Na plus. Respect to salt is obtained. Whenever the geminal dihalide, the carbon to which 2 halogen is connected, if that is a terminal carbon where hydrogen is also there, in that case you will get respect to salts. If it is a non-terminal, geminal dihalide, in that case you will get respective alkyne, because alkynes can also further react. Yes or no? Yeah, this is what I was talking about, geminal dihalide, where the terminal alkyne can be obtained. RCH2 CH Br, NaNH2 it forms RCH double bond CH Br. Further treatment with NaNH2, RC triple bond CH. Further treatment with NaNH2 will form RC triple bond C minus Na plus, and ammonia is released. Is that clear, students?
Yes, sir.
And what is the electronegativity of sp hybridized carbon?
3.5.
3.25. sp hybridized carbon is more electronegative than nitrogen and less electronegative than oxygen. sp2 hybridized carbon is having electronegativity of 2.75, which is less electronegative than nitrogen also. From calcium carbide, as I have told you, what type of reaction? It is a commercial method actually. Calcium carbide CaC2 will react with water to form C2H2, that is acetylene, and CaOH taken twice is obtained. On industrial scale, ethine is prepared by treating calcium carbide with water. CaC2 plus H2O will form HC triple bond CH plus CaOH taken twice. CaC2 plus D2O. D2O whenever you are taken, all the deuteriums are going to be present. So C2D2 is obtained, that is DC triple bond CD. DC triple bond CD plus CaOD taken twice. And how is this CaC2 is obtained? CaC2 will have this structure like Ca plus 2 will have electrostatic force of attraction with a C2 minus ion, and CaC2 is obtained by heating limestone and producing CaO, which is further treated with a carbon. Okay, that limestone is again further treated with a carbon. Is that clear, students?
Yes, sir.
Next, preparation of acetylene, CHCl3 or CHI3. As we have seen this reaction, CHCl3 will react with Ag, silver powder. It will form HC triple bond CH in the presence of heating. CHCl3 plus Ag, upon heating, it will form HC triple bond CH, and AgCl is going to be obtained. All the chlorines are going to be lost in the form of chloride ion Cl minus, and Ag will be converted to Ag plus. So we'll get a 6 moles of AgCl lost. You have to treat this with a acetylene. You have to prepare means you can treat a chloroform with the silver powder in the presence of high temperature. Okay, these are the methods of preparations of alkynes, and alkynes also have different types of reactions. What extra type of reaction alkynes will show when compared to alkenes? Can we think of? Alkynes, because of the presence of pi electron density similar to alkenes, will show addition reactions. That is true. But except apart from alkenes, alkynes will have a terminal alkynes will generally are acidic in nature, and they show some acid-base reactions. Alkenes will not show such type of reactions. Let us look at the reactivity, physical properties, and chemical properties as well. So physical properties, first members are gases, next 8 members are liquids, and higher ones are solids, because van der Waals forces changes, because molecular weight is directly proportional to van der Waals force of attraction. Molecular weight is directly proportional to van der Waals force of attraction. Ethine has characteristic order, other members are orderless. Ethine has characteristic order, other members are orderless. Alkynes are weakly polar in nature. so insoluble with water. But alkynes are weakly polar in nature, not greatly polar. So that is why they are less soluble or insoluble in water. Water is polar, and we all know like dissolves in like. And they are soluble in non-polar solvents like carbon tetrachloride, CCl4, benzene, and ether. Their melting point, boiling point, and density increase with increase in molar mass. Obviously, that is true because with increase in molar mass, van der Waals force of attraction increases. Van der Waals force of attraction increases, boiling point should increase, and melting point is mainly depending upon the crystal lattice structure. If you have a symmetrical alkane, it will have more melting point because it fits properly in that particular crystal lattice site, right? And mass increasing, so density should also be increasing. If you look at alkynes, they will undergo two types of reactions: addition reactions or C triple bond Cr, and reactions of terminal alkynes. Terminal alkynes are acidic in nature because it is sp hybridized carbon. Sp hybridized carbon will have an electronegativity of 3.25, so that CH bond becomes polar. So these are the extra type of reaction shown by alkynes apart from alkenes. So that is what I have told you. They will show addition reactions because they also have the pi electron density. But when compared to the alkenes, there the reaction conditions, they are going to be slightly changed because we have two double bonds in the respect to alkane. First reaction in alkenes, what we have studied: addition of halogen acids like HX. Addition of halogen acids we have studied in alkenes. The same halogen acids can be added to alkynes. But how many moles we can add? Earlier in the alkene, we have added only one molecule of halogen acid, like HCl or HBr. But here we have two pi bonds. Can I say two molecules of halogen acids can be added?
Yes, sir.
First reaction you can think of is addition of HX. So I take an alkene. Alkene, what alkene I will take? CH3, C triple bond CH. Let us take CH3, C triple bond CH. Propine upon react with HX, HCl or HBr or HI, not HF, because HF is not going to be greatly reacting with this molecule because it has stronger overlapping, so strong bond. So let us take HCl. So the pi electron density attacks H plus, hydrogen chlorine bond leaves. So as soon as this reaction occurs, we will generate CH3C, C double bond CH2, because pi electron density attacks proton. So we have carbon, triple bond carbon has been now converted to double bond carbon, carbon double bond carbon. This carbon will now attack the hydrogen. So it has two CH bonds now, and electron density from the middle carbon has been lost. So that will get a positive charge. Just like a vinyl carbocation is obtained, which you cannot rearrange. The carbon, unsaturated carbon atoms can never rearrange. I have told you yesterday, rearrangements are not possible for this particular carbocation. Now it will be attacking the chloride ion, right? We have taken HCl, so chloride ion which was there in the reaction mixture, that Cl minus will try to attack this particular carbon, generating CH3, CCl, double bond CH2. And now if you look at the other molecule of HCl, again the pi electron density attacks the proton, loss of chloride ion occurs, will generate CH3, CCl, positive charge, CH3. And now this is going to be finally attacked by one more chloride ion. The chloride ion will attack this particular carbon, generating CH3, CCl, CCl, CH3. This is your major product. Like two molecules are going to be added, generating, what is the name of this? 2,2 dichloropropane. Yes or no? 2,2 dichloropropane. Like whenever we have alkyne, two molecules of HX are going to be added. In alkane, only one double bond is there, so only one molecule has been added. That is the first type of reaction, addition of halogen acids. Addition of halogen acids. Right, students? So the same reaction we are talking about. Addition of halogen acids, two molecules of hydrogen halides, HCl, HBr, HI, adds to alkyne to form geminal dihalides. Geminal dihalides are obviously obtained because to the same carbon atom, two halogens are connected. If you take HC triple bond CH plus HBr, it will form CH2 double bond CHBr. That will again react with one more molecule to form CH3 CHBr2, 1 comma 1 dibromoethane. If you take propine, it will react with a HBr, 2 molecules to form 2 comma 2 dibromopropane. This is nothing but a major product. The same mechanism, whatever we have written. Yes or no, students?
Yes, sir.
Yes, sir.
Right, very good. In the addition of HX to vinyl halide we have taken. Okay, let us take vinyl halide means CH2 double bond CHX. X is some halogen. The halogen attached itself to the carbon atom on which halogen atom is already present. If you take a vinyl halide and if you try to add HX, like I am trying to add HX to vinyl halide, like I can take CH3 CHCl and I am adding HCl. Okay, CH3 CHCl and I am adding HCl. The pi electron density will attack H plus. As soon as the pi electron density attacks, where you will generate, what type of system you will generate? You can have two possibilities. One is CH2 plus CH2Cl. Other is CH3 CH plus Cl. Yes or no? These are the two types of possibilities. The electron density attack from this carbon or the other carbon. But out of these two carbocations, which carbocation is more stable?
CH2 plus CH2C.
Why? If you think of chlorine, it is an
Positive
inactive effect.
charge and chlorine.
Yeah. If you think of chlorine, it will withdraw the electron density by
Inductive effect.
inductive effect. So if you think of inductive effect, which should be more stable? Like I'll give you 1 and 2. This is your 1. This is your 2. So if inductive effect, if you consider chlorine withdraw the electron density, if chlorine is withdrawing the electron density in the 1, the positive charge should increase. If positive charge is increasing, its stability is going to be decreasing.
Yes.
But in 2, the chlorine is away, so it should be more stable. If you consider only inductive effect. But chlorine has a lone pair of electron or not? Chlorine possesses a lone pair of electron or not? Yes or no?
Yes, sir.
Chlorine possesses a
Yes.
lone pair of electron. The lone pair of electrons and positive charge, they can be in resonance. If you include that resonance, you will get CH3, CH double bond Cl. Chlorine will have two lone pairs and a positive charge. Now think of this particular stability of compound 1. Every atom has octet or not?
Yes,
8,
sir.
8. So chlorine also has two lone pairs, 2 bonds. The center atom, middle carbon atom, CH bond, CC bond, and carbon chlorine double bond, 4 bonds, so 8 electrons. This terminal carbon also has 3 CH bonds and 1 CC bond, 8 electrons. Whereas if you try to write the resonating structure of compound 1, you are getting a compound resonating structure where octet is completely satisfied, so 1 is more stable. So it should be more stable. If you think of only inductive effect, according to inductive effect, 1 should be less stable. But in reality, this compound 1 is more stable. Why? Because of back bonding, where you are getting the resonating structure, and that resonating structure is having complete octet. Okay.
Okay.
CH2 double bond CHCl attacking the H plus. The two possibilities are CH2 plus CH2Cl and CH2H CH plus Cl. It is resonance stabilized. Resonance stabilized. And since it is resonance stabilized, that is now going to be attacked by chloride ion. The chloride ion will be attacking this particular carbon. The chloride ion attacks this particular carbon, generating geminal dihalides. CH3, CHCl, CHCl. That's what we are saying. In the addition of HX to vinyl halide, the halogen atom, the halogen will attach to that particular carbon atom on which halogen is already present. Okay, it will lead to the formation of, you should not think like geminal dihalides are not going to be formed because of repulsions between the two halogen atoms. Okay. Why you should not think like that? Repulsions are there everywhere. The reaction proceeds to that particular transition state, that particular intermediate, which is more stable. Understanding this point or not? Two chlorines, you may ask a question, sir, both the chlorines are on the same carbon. Do they repel? Yes, they do repel. Because both the chlorines have lone pair of electrons. Both the chlorines are large in size. Repulsion is there always. But Just based on repulsions, you cannot say the final product. The reaction is proceeding through that path where the transition state or the intermediate is more stabilized. The intermediate which is more stable, that is formed first, later that is attacked by chloride ion. This is going to be the rate determining step, the formation of intermediate, not the attack of chloride ion to the particular carbon atom. Got it, students? Is that clear or not?
Yes, sir.
So organic chemistry you have to understand carefully. Everywhere you seem like some concepts are going to be like you can lead to different other product. What I mean to say is, if you neglect one concept, everything might be known to you if you study separately. If you neglect one concept, with respect to that, you will be getting different other products, which seems to be correct only. Misleading, it's actually. Addition of halogens, CH3, C triple bond, CH plus Br2 in the presence of CCl4. Addition of halogens to alkynes will happen in the presence of a non-polar solvent. And can I say, like we have to do this reaction in the presence of non-polar solvent or polar solvent, and why? If you do the reaction in non-polar solvent, this non-polar solvent will not try to act as a nucleophile, and it will not attack the any three-membered cyclic halonium ion. The reaction proceeds through what? Reaction proceeds through, because we are trying to add an electrophile which has lone pair of electron. Whenever you are trying to add an electrophile which has lone pair of electron, the reaction proceeds through cyclic halonium ion. Cyclic halonium ion formation. So cyclic halonium ion is formed. Then the Br minus, the bromide ion will act as a nucleophile, attacks the electrophilic carbon. You get 1, 2 dibromopropene. That will again attack with one more molecule of Br2 in the presence of CCl4 to form 1, 1, 2, 2 tetrabromopropane. Yes or no? So addition of bromine to alkyne will happen twice, because in alkynes we have 2 pi bonds. And can I use this as a test of unsaturation?
Yes.
Because the
Yes.
bromine is actually reddish in color or reddish orange in color. That color is going to be lost because bromine has been reacted with alkene. So loss of color indicates the presence of unsaturation in that particular compound. So reddish orange color of solution of bromine in carbon tetrachloride is decolorized. I am mentioning the solvent as carbon tetrachloride non-polar solvent. Non-polar solvent. Reddish orange color of solution of bromine in carbon tetrachloride is decolorized. So this reaction is used as test of unsaturation. Test of unsaturation. Try to solve some examples. Which of the following compounds will decolorize? Test of unsaturation. Which compound, students?
All are having unsaturation linkage.
Write down benzene and its derivatives. Benzene and its derivatives. Will not undergo electrophilic addition reactions, and thus they will not decolorize, or they will not give positive test for positive test for bromine water and Bayer's reagents. Okay, Bromine will not undergo electrophilic addition reactions. All these reactions, the Br2 addition, KMnO4 addition is electrophilic addition or base agent is oxidation. Such reactions will not be shown by benzene and its derivatives. Remaining compounds will show. Next compound is addition of water. Like alkanes and alkenes, alkynes are also immiscible and do not react with water. Immiscible means they are not soluble. However, one molecule of water adds to alkynes on warming with mercuric sulfate and dilute sulfuric acid at a 333 Kelvin to form carbonyl compounds. Mercuric sulfate, yesterday also I have told you, whenever you see Hg2 salt or mercury sulfate, immediately you have to understand that addition of water is happening. What is the role of mercury in this particular reaction?
It acts as catalyst.
Catalyst in this particular reaction. Why a catalyst is required? Because if you take an alkane like CH3 C triple bond CH, CH3 C triple bond CH, we are treating this with a H plus ion. So pi electron instead acts H plus. You will get what? CH3 C double bond CH2 plus, which is nothing but a vinyl carbocation. Vinyl carbocation is that stable?
No, sir.
So vinyl carbocations are less stable when compared to your normal 2-degree or 3-degree carbocations or benzoylic or allylic carbocations. Vinyl carbocations, aryl carbocations are unstable because sp2 hybridized carbon, which is electronegative, that is bearing a positive charge. So that is why what you can say is alkynes cannot form the vinyl carbocations easily, even though we have acid medium. So to catalyze this particular reaction, we need Hg2 salt. Okay, to catalyze this particular reaction, we need Hg2 salt. Hg2 salts, Hg2 will actually catalyze the reaction. And you get a CH2, like once this vinyl carbocation is formed, then attack of water being a nucleophilic in nature, it will attack its lone pair of electron, H2O, lone pair of electrons present on oxygen. They will be attacking this particular carbon atom. As soon as they attack, they form CH3COH2 with one lone pair and a positive charge, double bond CH2. Loss of H plus occurs, you will get a CH3COH, double bond CH2. Now you got a enol system. That enol will tautomerize to form respect to ketone. CH3C double bond O CH3 is obtained. This is nothing but your ketone. Okay. So whenever you try to add water to your alkyne, you will always get the enol form. The enol form can be tautomerized to keto form. So carbonyl compounds are obtained as the major products. Okay. So to form carbonyl compounds, that is important. Propine, if you take, as we have taken propine, we get what? You get respect to CH3, C double bond of CH3. So this is an indirect method of preparation of carbonyl compounds. Carbonyl compounds can be obtained from alkynes whenever water is added to alkyne. Addition of water to alkyne can be adding in the mercuric 2 salts, or can I do hydroboration oxidation or not, students? Hydroboration oxidation, oxymercuration, demercuration can also be done to alkyne. Hydroboration oxidation, oxymercuration, demercuration, whatever rules we apply for alkene, they are still applicable to alkyne. Alkyls will undergo addition of water according to anti-Markovnikov rule in hydroboration oxidation, according to Markovnikov rule in oxymercuration, demercuration, and they will form respective carbonyl compounds because of tautomerase structures. Because of tautomerase structures, right?
Yes.
Then reaction of terminal alkynes R C triple bond CH. Reaction with sodium. Terminal alkynes are acidic in nature, so they will undergo some acid-base reaction. Like you take R C triple bond CH, sodium is a very strong base, and alkyne is acid. Although we call it an acid, it is a weak acid. Sodium react with a sodium like R C triple bond CH will be reacting with a Na. Na has a tendency to undergo Na oxidation, that is Na plus and loss of electron. And this alkyne will undergo the cleavage of CH bond, forming R C triple bond C minus plus H plus. So what happens ultimately? R C triple bond C minus will be reacting with Na plus to form R C triple bond C minus Na plus, C minus Na plus, and H plus will take up an electron, whatever lost by sodium, to form hydrogen atom. Two such hydrogen atoms will combine with each other to form H2 gas. So you can say RC triple bond CH plus Na will give RC triple bond C minus Na plus half mole of H2. Plus half mole of H2. So it should have acidic proton. So will the second molecule react? No acidic proton. No acidic proton. So it is not a terminal alkyne. If there is no acidic proton, there is no reaction with the sodium to form respective salts. It is simple acid-base reaction. It is a simple acid-base reaction from where you can understand. You can actually calculate the amount of H2 gas obtained also. CH3 C triple bond CH plus Na, it will form CH3 C triple bond C minus Na plus half mole of H2. You may ask a question, sir, does alkyne directly undergo cleavage of CH bond? This reaction, although I am writing in this fashion, it is not happening by its own. It is happening just because of the presence of sodium. If sodium is not there, the CH bond will not cleave automatically. It remains as terminal alkane. Because sodium is there, which is acting as a very strong base, that base is actually making this proton acidic and remove the proton, and that proton is reacting with the electron to form hydrogen atom, which combines later to form H2 gas. Is that clear, students?
Yes, sir.
Yes.
Yes, right. Reaction with Tollens reagent. Tollens reagent is what? Tollens reagent is ammonical silver nitrate solution. So AgNO3 plus NH4OH. Ammonical silver nitrate. AgNO3 plus NH4OH, it can also be mentioned. They can also mention Ag2O. They can also mention AgNH3 taken twice whole plus. All the three ways are mentioning, all the three ways are same to mention the Tollens reagent. Because AgNO3 and H4OH will again react with each other to form the complex. The complex will again give Ag2O. All the three notations are same, representing Tollens reagent. Tollens reagent will do what? Tollens reagent will also react with the acidic proton, that is terminal alkynes, and whatever the Ag plus we have, that Ag plus will react with C minus to form some white PPT. And the NO3 minus whatever you have, that will react with NH4 plus. The NH4 plus will react with NO3 minus to form NH4OH. The OH minus whatever it is there, that will pick up the proton to form H2O. Reaction goes like this: RC triple bond CH plus AgNO3 plus NH4OH. The OH minus will pick up the proton, RC triple bond C minus Ag plus, NH4 plus NO3 minus NH4NO3, ammonium nitrate, OH minus picks up the proton, so to form water. And this particular salt is a white precipitate, white PPT. Okay, AgNO3 plus NH4OH will react with terminal alkyne to form white precipitate. So that is also the reaction of terminal alkyne with the Tollens reagent or ammonical silver nitrate solution. And if we take a non-terminal alkyne, will that reaction happen? Non-terminal alkyne or alkene?
No, sir.
Non-terminal alkyne, no acidic proton. Alkene also no reaction because no acidic proton. No acidic proton. So no reaction is going to be happening with the alkyne, non-terminal alkyne as well as alkene. Is that clear, students? Everything clear?
Yes, sir.
Yes. Yes.
Same reaction you can have with ammonical cuprous chloride, Cu2Cl2 and NH4OH. With the non-terminal alkynes, it will not react. With the terminal alkynes, it will form red precipitate. And alkene and a non-terminal alkyne, no acidic proton. No acidic proton means no reaction. Whenever we have a terminal alkyne, we have acidic proton. Acidic proton. Same type of reaction. OH minus picks up the proton to form water. NH4 plus and Cl minus to form NH4Cl. And you will get RC double bond C minus Cu plus, which is a red PPT. which is a red PPT. Earlier we have R C triple bond C minus Ag plus, which is a white PPT. So that was the major difference. Ammonical cuprous chloride solution, Tollens reagent, and NaNH2 will be reacting with the terminal alkynes, and they will undergo some acid-base reactions, right? So same, we can look at the animation also. So then you can have the polymerization reaction. Polymerization means addition of monomers, many number of monomers to form the respective polymer. So you can have linear polymerization as the first case. Linear polymerization means, like under suitable conditions, linear polymerization of ethine takes place to produce polyacetylene or polyethine, which is a high molecular weight polyethylene or polyene. So how that reaction is going to happen? So we have CH triple bond CH. You cannot write the reaction in this manner like CH double bond CH. This is repeating n times. First, the two molecules of acetylene will be fused. CH triple bond CH, CH triple bond CH. This carbon and the other carbon, whatever the pi electron density we have, they are combined. So you'll get a CH double bond CH. This carbon and the other carbon, they are going to be combined with single bond. So the pi bond is lost. And you have double bond CH. And these two terminal carbons are repeated. So this is nothing but your repeating molecule. This is the repeating unit. If this is repeated, the electronic repulsions would be high. Here, pi electron density repulsions will destabilize. That's why CH double bond CH, it cannot be repeated n times. That is not formed. So generally unsaturated hydrocarbons undergo addition polymerations. Okay, unsaturated hydrocarbons undergoes addition polymerization. Addition polymerization means the molecules are just added. There are no loss of some simple molecules. So that is how you are getting polyethylene. So polyethylene, in the polyethylene, two molecules of acetylene combine first to form a repeating unit, which is CH double bond CH, CH double bond CH, because here the repulsions are minimized. If you try to write the repeating unit in this manner, like we have written for ethene, that would be wrong. Is that clear, students?
Yes.
And the last type of polymerization of alkane is cyclic polymerization. Ethine on passing through red hot iron tube at 873 Kelvin, you have to remember these conditions. Red hot iron tube or copper tube at 873 Kelvin undergoes cyclic polymerization to form benzene. So benzene is nothing but an aromatic hydrocarbon. So CH triple bond CH, these bonds are going to be moved in this fashion to form respective benzene. So if you take 3 moles of CH3, C triple bond CH, what you will get? What you will get in this case?
One comma 3,5 trimethyl benzene.
Yes, you will be getting this type of product. What is the other name of this particular product? 1 comma 3 comma 5 trimethyl benzene, that is also called as mesitylene. Okay, 1 comma 3 comma 5 trimethyl benzene or mesitylene is obtained. Is that clear, students? Is everything clear so far? Yes or no?
Yes.
Yes. Right, then we'll stop our discussion for today. Tomorrow we'll be continuing with the next set of reactions like aromatic hydrocarbons, and then start with the haloalkanes, haloarenes, alcohols, phenols, ethers, like that we'll proceed. Right. Thank you all, everyone. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.